Picture a comet, a mountain of dirty ice drifting through a sky with no air and no sound. It has been traveling for longer than human civilization has existed. When it finally crosses into the inner solar system and catches the sun's light, it traces a tail across Earth's night sky. That comet came from roughly 50,000 astronomical units away, nearly a full light year from the sun. But here is what most people don't realize. That comet never left our solar system. Our solar system extends that far. There is a vast shell of icy bodies surrounding the sun at distances reaching almost halfway to the nearest star. Every long-period comet that has ever appeared in Earth's sky fell inward from that shell. We call it the Oort Cloud. And the reason it breaks human imagination is not because it is violent or strange. It is because it is simply, honestly, larger than any frame of reference we have ever constructed to hold it. If you enjoy deep space and science content, do me a small favor, hit that like button and subscribe. It genuinely helps this channel grow. Get yourself comfortable. Let's begin. For most of human history, the edge of the solar system was wherever the last known planet happened to be. That edge kept moving outward. Every time someone built a better instrument or looked a little longer at the night sky, the boundary pushed further. Uranus, discovered in 1781 by William Herschel using a telescope he had ground himself in his own backyard, extended the known solar system almost twice as far as Saturn. It nearly doubled the map in a single observation. Neptune, found in 1846 by Johann Galle, working from orbital predictions made by Urbain Le Verrier, pushed it further still. Le Verrier had predicted Neptune's existence purely from the gravitational wobble it was inducing in Uranus's orbit. He told the observers where to point the telescope, and on the very first night of searching, there it was, within 1 degree of its predicted position. Pluto arrived in 1930, found by Clyde Tombaugh at the Lowell Observatory in Arizona after a painstaking multi-year search through photographic plates. Tombaugh blinked through thousands of image pairs by hand, comparing exposures taken days apart, watching for any point of light that had moved against the fixed background of stars. Each discovery added distance. Each one pushed the boundary a little further than the generation before had believed it went. And each time the map grew, whatever had seemed like the edge before turned out to be something else. A temporary stopping point, not the actual limit of anything. But all of those discoveries shared something in common. They were all found in roughly the same region of space, in a flat disk, orbiting the sun in more or less the same plane, confined to a structure you could, with some effort, represent on a single sheet of paper. The planets, the asteroid belt, even Pluto, they all sit within a relatively thin slice of space, extending out to maybe 40 or 50 astronomical units from the sun. 1 astronomical unit is the average distance from Earth to the sun, about 93 million miles. So 50 astronomical units is around 4.65 billion miles. That sounds like a lot. In ordinary human terms, it is an almost incomprehensible distance. But in the context of what we are about to discuss, 50 astronomical units is the front porch. Not the house, not the yard, just the front porch, the few steps immediately outside the door. Neptune sits at about 30 astronomical units from the sun. That is roughly 2.8 billion miles. The Voyager 2 spacecraft, launched in 1977, took 12 years just to reach Neptune. 12 years of constant motion in a near straight line, and it still had not left what most people would call the planetary solar system. Beyond Neptune, from about 30 to 55 astronomical units, lies the Kuiper Belt, a region of icy objects sitting in roughly the same orbital plane as the planets. Pluto lives there. So does Eris, Makemake, Haumea, and thousands of smaller bodies. The Kuiper Belt is the source of most short-period comets, the ones that swing around the Sun every few hundred years or less, arriving predictably from that same flat disk. Everything was in the disk. Everything pointed inward from the disk. The solar system was a flat system, and the flat system had an edge, and beyond the edge was nothing. That was the map. And for a long time, astronomers were broadly comfortable with it. It was incomplete in its details, but sound in its general shape. The planets formed a flat system. Space was mostly empty beyond them, and whatever lay further out was the domain of future telescopes and future questions, not urgent ones. That map was wrong, not slightly wrong, wrong in a way that took decades to understand and several more decades to fill in properly, wrong about the shape, the size, and the basic nature of the thing being described. The first clue was the comets, not the short-period ones from the Kuiper Belt, predictable, well-catalogued, arriving from the same general region of sky every time. The long-period ones, comets with orbital periods of thousands or millions of years, arriving on their very first pass through the inner solar system, objects that had never been this close to the Sun before in the entire 4.6 billion-year history of the solar system. These comets had two properties the disk model simply could not explain. First, they came from enormous distances, not dozens of astronomical units, but tens of thousands. Second, they came from every direction. Not just from the flat orbital plane of the planets, but from above it and below it, at angles that had nothing to do with the shared disk. If they were coming from a Kuiper Belt-style structure, they should mostly arrive from that disk's general direction. They did not. They arrived as though scattered randomly across a complete sphere surrounding the entire solar system, coming in from all elevations equally, with no preference for any particular patch of sky. That pattern was a problem. A flat disk cannot produce a spherical arrival pattern. Something outside the disk, something surrounding it in all directions simultaneously, had to be the source. The disk model of the solar system could not account for these comets. The model was missing something large, very large. To understand why this was disorienting, it helps to think about what a comet is and what happens to it over time. A comet is a small body, typically a few kilometers across, made mostly of ice mixed with rock and dust. When a comet enters the inner solar system and gets close enough to the Sun, the ice sublimates. It converts directly from solid to gas, releasing material that streams away to form the glowing coma and the tail visible from Earth. That process is destructive. Every pass through the inner solar system costs a comet some of its mass. A comet making repeated close approaches to the Sun does not last indefinitely. It loses material with each orbit, gradually diminishes, and eventually breaks apart or fades into a dark, inert object that no longer behaves like a comet at all. This creates a specific problem the disk model could not resolve. Long-period comets arriving on their first inner solar system pass are pristine. They have not made this trip before, and their surfaces preserve material essentially undisturbed since the solar system formed, but they are already losing that material on this very first approach. Over geological time, repeated visits would destroy them completely. That means they cannot have been circling the inner solar system since the beginning. They must have spent most of their existence somewhere far away, cold and undisturbed, waiting for something to push them inward. And they must keep arriving continuously across billions of years, which means the reservoir supplying them must be vast, large enough to have been feeding this process since the solar system was young, and still capable of doing so today. Big enough that billions of years of continuous depletion has not visibly put a dent in it. Something had to be out there. The comets themselves were the evidence. What remained was locating it, describing its size, its shape, its distance, from nothing but the backward traced trajectories of falling ice. That required someone willing to sit with the numbers and follow them wherever they led. Astronomers in the early 20th century understood the problem. The Estonian astronomer Ernst Öpik had gestured at a possible solution as early as 1932, suggesting that a distant reservoir of cometary bodies must exist at the far outer edges of the solar system. Öpik reasoned that because comets lose material during inner solar system passes, there had to be a source continuously replacing them, something that had been producing fresh comets for billions of years without running noticeably low. His reasoning was sound, but his idea had no numbers, a direction rather than a destination, a suggestion you could nod at without being able to test. The numbers came 18 years later, in 1950, from a desk at the Leiden Observatory in the Netherlands, from a man working with a list of 19 comets and the patience to trace every one of their orbits backward to the point where each one began. What he found did not extend the existing map by some additional comfortable margin. It made the old map look like a diagram of a single room, drawn as though the room were the whole building. Not a disk of planets with empty space surrounding it, but something more like a sphere, an enormous, nearly invisible gravitational territory extending in every direction, containing trillions of objects no telescope in 1950 could detect, reaching into the dark far beyond anything the words solar system had ever been built to hold. Every planet we know, Earth, Mars, Jupiter, Saturn, distant Neptune, sits inside a small warm region at the center of something much larger and much quieter. That region is where the sunlight falls and where the heat is felt, where every human life has ever been lived, and where every spacecraft ever launched has spent essentially its entire existence. What lies beyond it belongs to a different kind of dark. And it was waiting in 1950 for one man at a desk in Leiden to give it a name and a set of numbers that would hold up for the next 75 years. Jan Hendrik Oort was born in 1900 in the Netherlands and spent most of his working life at the Leiden Observatory. By 1950, he was already one of the most respected astronomers in the world. He had calculated the Sun's distance from the center of the Milky Way, about 26,000 light-years, a figure we still use today. He had worked out the rate at which the Sun orbits the galactic center, roughly once every 225 million years. He had done foundational work on the structure of the galaxy itself, helping map the spiral arms using radio wave emissions from interstellar hydrogen. He was not a young theorist looking to make a name. He was an established scientist with decades of careful work behind him. The comet question was, for him, a side project, something to think about between more pressing matters. In 1950, he published a paper in the Bulletin of the Astronomical Institute of the Netherlands. The title was plain: The Structure of the Cloud of Comets Surrounding the Solar System and a Hypothesis Concerning Its Origin. The contents were anything but plain. What Oort did was methodical. He compiled orbital data for 19 long-period comets, whose paths had been carefully observed and recorded. For each one, he worked backward from the observed trajectory to calculate the original orbit, the orbit the comet had before it entered the inner solar system and was slightly deflected by the gravitational pull of the planets along the way. That correction mattered because Oort was not asking where the comets currently were. He was asking where they came from before anyone had ever seen them. When he mapped the results, a pattern came through. 10 of the 19 comets, more than half, showed original orbits that traced back to distances of around 44,000 astronomical units from the Sun. 44,000 astronomical units. That is roughly 0.7 light years. That is a distance so large that light itself, traveling at 671 million miles per hour, would take more than 8 months to cross it. At the scale of the inner solar system, where Earth sits at 1 astronomical unit and Mars at about 1.5 astronomical units, 44,000 astronomical units is not a nearby structure. It exists in a part of space the word nearby was never designed to reach. And the orbits pointed inward from all directions, not from a disk, from a sphere. The comets were falling toward the Sun from every angle, from every elevation, with no preference for the flat orbital plane the planets share. Whatever was sitting out there at 44,000 astronomical units had to surround the Sun completely, not just extend from one side, not confined to any particular region of sky. A cloud, a spherical shell of icy bodies, sitting at distances that dwarfed everything previously included in the solar system map, falling inward occasionally when something nudged them out of their long, cold orbits. Oort was careful about what he was claiming. He acknowledged that 19 comets was a small sample. He noted that the backward calculation involved assumptions that could introduce errors. He did not state his conclusion as certainty, but the pattern was there, consistent across the data he had, and he followed it where it led. He proposed that the solar system was surrounded by a vast, roughly spherical reservoir of cometary bodies extending out to perhaps 150,000 astronomical units, close to 2.4 light years, and that long-period comets were objects dislodged from this reservoir by the gravitational influence of passing stars, sent plunging inward for the first time in their existence. The scientific community, over the following years and decades, largely accepted it. Not because the cloud had been directly detected. It never has been, not to this day, and no telescope currently in existence is capable of imaging it directly. But no alternative explanation could account for the pattern Oort had found. The comets had to be coming from somewhere. The backward traced orbits pointed to a specific somewhere. And that somewhere was enormous. To put the distance in some kind of human frame, 44,000 astronomical units is roughly 4.1 trillion miles. If you could drive at 65 miles per hour without stopping, it would take about 7.2 billion years to cover that distance. The Sun itself is only about 4.6 billion years old. A car that had started driving at the moment the solar system formed would not yet have reached the inner concentration of the Oort Cloud. It would still be on the way, with no arrival in sight. These are not comfortable numbers. They do not correspond to anything in ordinary experience. A light year is not a unit that means something in the same way a mile or a kilometer means something. It requires conversion after conversion before it begins to approach anything felt. And even then, it only approaches. It does not arrive. Picture the scene at Leiden Observatory in 1950. The building sits in the center of a Dutch city, surrounded by canals and narrow streets and ordinary life. Inside, a man at a desk with a list of 19 comets works through the backward mathematics, one comet at a time. He is not looking through a telescope. He is not observing anything directly. He is doing arithmetic on comet tables, correcting for planetary perturbations, converting observed trajectories into original ones, mapping origins on a scale that no human eye has ever seen and no instrument has ever reached. And from that arithmetic, from that specific quiet calculation at a desk in the Netherlands, comes a description of the largest structure in the solar system. An object that extends from here to nearly halfway to the nearest star. An object containing trillions of bodies. An object that has been sitting there, surrounding our Sun, since before the Earth had oceans. Described for the first time by a man doing math by hand, with 19 data points and the patience to follow them all the way out. But Oort had described only where the cloud was, and roughly how far it extended. He had not explained why it was spherical rather than flat. He had not explained what the objects inside it were made of, how they got there, or what forces kept them in orbits so distant and so slow that a single trip around the Sun took millions of years. Those questions pointed somewhere else. They pointed backward, all the way to the beginning of the solar system, and forward toward forces larger than the Sun itself. Which means we have only just started. The distance from the Sun to the inner edge of the Oort Cloud is somewhere between 2,000 and 5,000 astronomical units. The outer edge sits at around 100,000 astronomical units, though some models push that to 200,000. These numbers appear in papers and textbooks regularly. What they do not do on first encounter is mean anything. So let us try to build them out of something that does. 1 astronomical unit is 93 million miles. That is the distance from Earth to the Sun. Light covers it in about 8 minutes and 20 seconds. New Horizons, the spacecraft that flew past Pluto in 2015, takes about 5 hours to cross 1 astronomical unit at its cruising speed. At 65 miles an hour in a car, it would take roughly 163 years. That is 1 astronomical unit, a single unit of the measurement system we are about to stretch to its limit. Now multiply by 100,000. The outer edge of the Oort Cloud sits at roughly 100,000 astronomical units from the Sun. That is 9.3 trillion miles. In light travel time, that is about 1.6 light years. Light leaving the Sun right now will not reach the outer edge of the Oort Cloud for roughly a year and a half. In Voyager 1 terms, and Voyager 1 is the most distant human-made object ever built, launched in 1977 and now sitting at roughly 165 astronomical units from the Sun after nearly 50 years of travel, the outer edge of the Oort Cloud is about 600 times further away than Voyager 1 has ever been. Voyager 1 will not reach the inner edge of the Oort Cloud for approximately 300 more years. It will not exit the outer edge for approximately 30,000 years. By that point, its nuclear power source will have been dead for nearly 3 centuries. It will pass through the Oort Cloud in complete silence, with no instruments running and no signal going anywhere. A piece of human machinery drifting through a structure it was never built to reach. NASA describes the sunlight timeline this way. Light leaving the Sun takes 8 minutes and 20 seconds to reach Earth. It takes about 4 hours and 40 minutes to reach Neptune. It takes between 10 and 28 days to reach the inner edge of the Oort Cloud, and it takes up to a year and a half to pass beyond the outer edge. The difference between Neptune and the outer Oort Cloud, measured in light travel time, is the difference between 4.5 hours and 18 months. The planets we know, including the most distant one, are not even in the same order of magnitude as what the Oort Cloud occupies. The cloud is not a thin shell, it is a thick, spherical volume. The distance from its inner edge to its outer edge, the depth of the cloud itself, is on the order of 95,000 astronomical units. That is roughly 8.8 trillion miles of depth. You could fit the entire planetary solar system, everything from Mercury out to Neptune, inside the Oort Cloud's thickness roughly 3,000 times over. The cloud also comes in two distinct regions. The outer Oort Cloud, from roughly 20,000 to 100,000 astronomical units, is spherical. Objects orbit the Sun at every inclination, above, below, sideways, at angles that have nothing to do with the flat plane of the planets. This is why long-period comets arrive from every direction in the sky. The inner Oort Cloud, sometimes called the Hills Cloud, from roughly 2,000 to 20,000 astronomical units, is shaped more like a flattened torus, a wide donut rather than a full sphere. It is more densely packed than the outer cloud and likely holds 2 to 5 times as much mass, though no one has measured it precisely because no instrument has ever reached it. Objects in the inner cloud are more tightly bound to the Sun's gravity and harder to dislodge, which is why they produce fewer observable comets. They sit there in the dark, in that wide donut shape, mostly undisturbed. The outer cloud contains an estimated 1 trillion objects larger than 1 kilometer in diameter. 1 trillion. There are roughly 100 billion stars in the Milky Way galaxy. The outer Oort Cloud contains about 10 times as many objects above 1 kilometer in size as our galaxy has stars. And yet, despite that count, the cloud is so vast that the average separation between neighboring objects is on the order of tens of millions of kilometers, greater than the Earth-Moon distance, on average, between one piece of ice and the next nearest one. It is not a dense field of debris. It is almost entirely empty space, with objects spaced so far apart that a spacecraft traveling through it would have essentially no chance of stumbling across one. The total mass of the outer Oort Cloud is estimated at roughly 5 Earth masses. 5 Earth masses spread across a sphere almost 2 light-years across. What this means in practice is that the Oort Cloud, for all its staggering number of inhabitants, is one of the least dense structures in the entire solar system. It is enormous. It is also, in nearly every cubic kilometer of its volume, empty, a name for vast emptiness, loosely punctuated with ice. The nearest star to our Sun is Proxima Centauri, at 4.24 light-years. The outer edge of the Oort Cloud reaches somewhere between 1.6 and 3 light-years, depending on the estimate used. Our solar system does not end at Neptune. It does not end at the Kuiper Belt. It ends somewhere in the dark between here and there, at a boundary no instrument has directly seen, at a distance light needs over a year to cross. But this raises a question the size alone cannot answer. If the Oort Cloud is so large and contains so many objects, why has no one ever directly seen it? Why are all these numbers estimates? Why, after 75 years of improving telescopes and space-based observatories, do we still have no photograph of a single confirmed Oort Cloud object sitting in its natural orbit? The answer is one of the stranger facts in modern astronomy, and it starts not with what the cloud is, but with how dark and small and far away everything out there actually is. The Oort Cloud has never been directly observed. No telescope has ever photographed it. No spacecraft has ever visited it. No camera has ever returned an image of the vast reservoir sitting at the edge of the solar system. Every number associated with the Oort Cloud, its distance, its mass, its population, its structure, comes from inference, from comets that fell inward, from orbital mathematics, from computer models built to explain observations of objects that are not the Oort Cloud itself, but that had to come from somewhere. This is worth sitting with. The largest structure in the solar system, a region extending halfway to the nearest star, a shell containing an estimated trillion objects. It exists, from humanity's current observational standpoint, entirely as a conclusion. We have never seen it. We have only ever seen what it sends us. The reason is straightforward. Objects in the Oort Cloud are small, dark, and at distances that defeat current technology completely. A typical Oort Cloud object might be a few kilometers across, roughly the size of a small mountain. At a distance of 10,000 or 50,000 or 100,000 astronomical units, an object that size reflects almost no sunlight. The intensity of light falls off with the square of distance. At 50,000 astronomical units, the Sun is roughly 2.5 billion times dimmer than it appears from Earth. An object the size of a small mountain, reflecting a fraction of that already vanishingly faint light, produces a signal so weak that no telescope built so far could detect it. Even the largest objects that might exist in the Oort Cloud, perhaps a few hundred kilometers across, would be essentially invisible at those distances. Beyond the individual objects being dark and small, there is the spacing problem. A single cube of space, 1,000 astronomical units on each side, itself an almost unimaginably large volume, contains on average only about 2 Oort Cloud objects larger than 1 kilometer. The cloud is not a fog. You cannot photograph it as a structure. It is a near-total vacuum, very occasionally containing a piece of ancient ice, with each piece separated from its nearest neighbor by distances greater than the Earth-Moon gap. Even the most powerful telescope in existence, pointed directly at the outer solar system, would see nothing but darkness at those distances. What astronomers have instead are the comets. When something disturbs an Oort Cloud object, a passing star, the galactic tide, another body drifting nearby, the orbit shifts. Over thousands of years, the shift gradually steers the object inward. It falls. It crosses the outer solar system, continues past the Kuiper Belt region, moves in toward the planets. As it approaches the Sun and the ice begins to sublimate, it becomes a comet, glowing, visible, measurable. That comet carries information about where it came from. Its orbit, traced backward, points to its origin. That is how we know the Oort Cloud is there. Wait for the cloud to send something in and read the trajectory of the arrival. It is indirect, it is slow, and it depends entirely on the cloud cooperating by ejecting objects at a rate high enough to study. But it works. The pattern in arrival directions and the calculated original orbits of hundreds of long-period comets consistently points to the same vast spherical shell at the same enormous distances. The signal is clear. The source is real. We simply cannot see the source itself. In 2003, astronomers got the closest thing to a direct detection yet achieved. Michael Brown, Chad Trujillo, and David Rabinowitz, working at Palomar Observatory in California, discovered a small reddish object on an orbit unlike anything previously seen beyond the Kuiper Belt. They named it Sedna, after the Inuit goddess of the Arctic Ocean. Sedna's orbit is highly elliptical. At its closest approach to the Sun, it reaches about 76 astronomical units, and at its farthest, it swings out to around 937 astronomical units. Its orbital period is approximately 11,400 years. One single trip around the Sun takes Sedna longer than all of recorded human history, several times over. What made Sedna remarkable was that its orbit made no sense within the existing models. Its closest point to the Sun, 76 astronomical units, is well beyond Neptune's gravitational reach. Neptune cannot have scattered Sedna into that orbit. No known planet can explain how it got there. The distant mechanisms consistent with Sedna's position involved either a passing star early in the solar system's history or the gravitational influence of other stars during a period when the Sun was still embedded in a dense stellar cluster. Both explanations required the inner Oort cloud to exist, a population of bodies in the transition zone between the Kuiper Belt and the main cloud, perturbed into distant orbits during the solar system's formation. Sedna appeared to be the first observed member of that population. In 2012, a second object was found, designated 2012 VP113, with a closest approach to the Sun of about 80 astronomical units. Sedna was not a fluke. These objects occupy a region of space that should be empty if the inner Oort cloud does not exist, and their presence there is consistent with what the inner cloud predicts. Their orbits are what inner Oort cloud objects should look like. Their existence confirms the cloud's inner edge in a way that inward-falling comets alone could not. You are listening to a description of something no human instrument has ever photographed in its natural state. Every figure in this section, the trillion objects, the 5 Earth masses, the 100,000 astronomical units outer boundary, comes not from observation of the cloud itself, but from the comets it sends inward, from Sedna, from simulations of early solar system dynamics. The confidence behind those numbers is high. The direct evidence is 0. That is where the science currently stands. And understanding how that structure came to be there requires going back to a time before any of it existed. The disk cloud was not always where it is. Nothing in the solar system was always where it is. 4.5 billion years ago, there was no solar system at all. Only a slowly rotating cloud of gas and dust several light years across, gradually pulling itself inward under its own gravity. As it collapsed, it flattened. The center grew dense and hot until nuclear fusion ignited and the Sun was born. The remaining material in the disk, gas, dust, and the countless grains of rock and ice that had not fallen into the new star, began accumulating. Dust grains became pebbles, pebbles became boulders, boulders became planetesimals, objects ranging from meters to hundreds of kilometers across, orbiting the young Sun in their billions. Most of those planetesimals are gone now. Some built the planets, some built the asteroids, some were consumed by the growing worlds around them. But hundreds of billions of them, perhaps trillions, were thrown away. The culprit was gravity, specifically the gravity of the giant planets. Jupiter was forming at the same time as all of this debris was still circulating in the disk. As Jupiter grew, its gravitational reach extended further out. Any planetesimal that drifted too close to Jupiter got flung, either into a dramatically altered orbit, or, in many cases, out of the solar system entirely. Saturn did the same. So did Uranus and Neptune, as they migrated outward during the chaotic early period of solar system history. The giant planets were not passive neighbors. They were throwing material in every direction. Some of the ejected planetesimals gained enough velocity to escape the Sun's gravity entirely and drifted off into interstellar space, lost. But many did not quite escape. They had been thrown far, far enough that they were now at distances of tens of thousands of astronomical units. But they were still gravitationally bound to the Sun, still technically orbiting it, on paths so enormous that a single loop took millions of years to complete. These objects settled into the outer solar system, their highly elliptical orbits slowly shaped over time by a force that nobody in the inner solar system pays much attention to: the gravitational tide of the galaxy itself. The Milky Way is not a uniform gravitational field. Its mass is not evenly distributed. The galactic disk, the flat concentration of stars and gas that makes up most of the visible galaxy, pulls more strongly on the side of the Oort cloud, facing toward the galactic plane, than on the side facing away. This galactic tide is negligible at planetary distances, completely drowned out by the Sun's own gravity. But at 50,000 or 100,000 astronomical units from the Sun's gravity has thinned to almost nothing, and even the gentle background tide of the Milky Way matters. Over millions of years, this tide slowly reshapes the orbits of objects at those distances, pulling them away from the flat disk geometry they were ejected into and pushing them gradually into more spherical, randomly oriented paths. This is the reason the outer Oort Cloud is spherical. The planets flung the objects outward in a disk. The galaxy rounded the whole structure over time into a shell. The Sun also did not form alone. Current models of solar system formation hold that the Sun was born inside a dense cluster of somewhere between 200 and 400 stars, all forming from the same parent cloud within a relatively short span of time. This early stellar nursery would have been crowded by astronomical standards, stars passing within hundreds or even thousands of astronomical units of each other, as the cluster gradually dispersed over tens of millions of years. The gravitational interactions between these neighboring stars during that period played a role in shaping the Oort Cloud while its mass was at its peak. Models suggest that as much as half the material now sitting in the Oort Cloud may have originally formed around other stars in that early cluster, captured by the Sun's gravity as those stars moved away. The Sun eventually left the cluster, as most stars do. The companion stars spread across the galaxy, but the material, some of it originally foreign, formed around a different star, remained behind. Sitting in the outer solar system, slowly orbiting on paths that take millions of years to complete. The Oort Cloud's total mass peaked roughly 800 million years after the solar system formed. By then, the pace of ejection and accretion had slowed, and depletion, through comets falling inward, through objects stripped away by passing stars, through gradual loss to interstellar space, began to outpace the rate of new material arriving. The cloud has been slowly declining ever since. What exists today is a reduced version of what was there 4 billion years ago, still vast by any human scale, but a smaller inventory than the one originally assembled. What the cloud is made of reflects where those original planetesimals came from. The objects are mostly ice, water ice, methane ice, ethane ice, carbon monoxide, hydrogen cyanide, ammonia. The frozen chemistry of the early solar nebula, preserved at temperatures around -270 degrees Celsius, just a few degrees above the coldest temperature physically possible. These objects have been sitting at those temperatures in near complete darkness, essentially undisturbed, for 4.6 billion years. They are not processed material that has been through repeated heating cycles. They are old in a very specific sense. They are samples of the molecular cloud that became the solar system, kept in cold storage at the edge of what the Sun controls. When a comet falls inward from the Oort Cloud and scientists analyze its chemical composition, they are reading chemistry that formed before Earth existed, before the Moon formed, before any planet had taken its current shape. The Oort Cloud is the solar system's oldest unaltered material, and it has been sitting out there, largely untouched, while everything closer in formed and changed, and in one case, grew complicated enough to wonder about it. The question that follows is, what disturbs it? The objects are in stable orbits, far from the planets, at distances where the Sun's gravity is barely felt. What reaches that far and knocks something loose? What sends a body that has been undisturbed for billions of years suddenly falling inward toward the warmth it has never known? The answer involves forces operating on timescales that make all of human history look brief, and one of them is already on its way. The Oort Cloud sits at the precise edge of the Sun's gravitational control. At distances of 50,000 or 100,000 astronomical units, the Sun holds onto its objects by almost nothing. That is the defining characteristic of the outer cloud, not just its distance but its fragility. Objects out there are attached to the Sun by the thinnest possible gravitational thread, and almost anything can cut it. A slight push from any direction is enough to change an orbit that has been stable for millions of years. Three things provide that push: the galactic tide, passing stars, and giant molecular clouds, each operating on a different time scale, each reaching the cloud from a different direction, and together ensuring the cloud is never entirely at rest. The galactic tide is the most persistent, as the mass of the Milky Way creates a continuous gravitational gradient across the outer solar system, stronger on the side facing the galactic plane, slightly weaker on the side facing away. It slowly torques the orbits of Oort Cloud objects over millions of years, rotating their orbital planes and gradually altering the angles at which they approach the Sun at their closest points. For objects already on large, slow orbits, this gentle torquing can eventually bring their closest approach to the Sun into the inner solar system for the first time. When that happens, they fall inward. They become comets. Models suggest that up to 90% of all long-period comets entering the inner solar system may have been set in motion this way, not by any dramatic specific event, but by the quiet and continuous gravitational squeeze of the galaxy itself. The Milky Way is, patiently and without interruption, sending us comets. Passing stars are less continuous but more dramatic. Stars move through the galaxy at their own velocities, and occasionally one passes close enough to the Sun to meaningfully disturb the outer Oort cloud. A stellar passage at 10,000 astronomical units, well within the outer cloud's boundaries, can knock thousands of objects out of their stable orbits at once, sending some falling inward as comets and flinging others out of the solar system entirely into interstellar space. We know this has already happened recently, in astronomical terms. Roughly 70,000 years ago, a small binary star system known as Schultz's star passed through the outer Oort cloud at a distance of approximately 52,000 astronomical units from the Sun. It is a dim red dwarf about 86 times less massive than the Sun, and its low mass and high relative speed meant the encounter was brief. But it was real. A star came through the outer Oort cloud, while anatomically modern humans were already living on Earth. And the objects it dislodged may only now, 70,000 years later, be completing the long fall inward toward the Sun. A larger encounter is coming. A star called Gliese 710, currently about 63 light-years away, is moving toward the Sun. In approximately 1.3 million years, it is expected to pass within roughly 13,000 astronomical units, well inside the outer Oort cloud, and close enough that models predict a substantial increase in the comet flux reaching the inner solar system for a period of millions of years after the encounter. Gliese 710 is a K-type star, about 60% the mass of the Sun. Its passage will not be an event any living thing currently on Earth will witness. It will unfold across timescales longer than our species has existed, and the comets it sends inward will arrive long after. Whatever is living here then has had time to notice, but it is predictable, it is coming, and it represents the upper range of what routine stellar traffic in the solar neighborhood regularly produces. There have been more dramatic proposals. In 1984, the physicist Richard Muller suggested that the Sun might have an undiscovered companion, a dim red or brown dwarf on a very long elliptical orbit, passing through the Oort Cloud approximately every 26 million years and triggering periodic comet showers that some researchers had linked to mass extinction events on Earth. The hypothetical object was named Nemesis. The idea was appealing in its tidiness, a single mechanism explaining both the comet showers and the extinction pattern. But no evidence of Nemesis has ever been found. Extensive sky surveys have turned up nothing fitting the description, and more careful statistical analysis of the fossil record has cast doubt on whether the extinction periodicity was real in the first place. Current scientific consensus does not support the Nemesis hypothesis. It remains a proposal that the evidence did not confirm. What the evidence does confirm is a picture of the outer solar system as a place in constant, slow negotiation between the Sun's gravity and everything else. The galactic tide pulls, stars pass and push. Giant molecular clouds, vast concentrations of dense gas that the solar system occasionally drifts through during its orbit around the galactic center, add additional less predictable perturbations when the solar system enters a denser region of the galaxy. The Oort Cloud responds to all of it, continuously, across timescales that make human civilization look like a brief interruption. Every comet that has ever appeared in Earth's sky is the end product of this process. Halley's Comet, observed from Earth since at least 240 BC, making its 75 to 76-year loop reliably enough that ancient civilizations catalogued it, began somewhere in the outer solar system before being drawn into its current short period. Comet Hale-Bopp, one of the brightest comets of the 20th century, visible to the naked eye throughout 1997, came from the Oort Cloud on an original orbit that placed its previous closest approach to the Sun around 4,200 years before its 1997 arrival. It had been traveling since roughly 2200 BC, Comet West in 1976, Comet Lovejoy in 2011, the long list of unnamed objects that lit up the sky for weeks and then continued on their way. Each one spent billions of years in cold storage in the outer solar system. And then something moved it. A tide, a passing star, a shift in orbital plane too small to measure from here. And it fell. There is one angle on the Oort Cloud that almost no discussion ever reaches. Every comet that has arrived in our sky has made an actual journey across actual distance, taking actual time. What does that crossing look like? Not in light years or astronomical units, but measured against the only scale of motion humans have ever had direct experience with, the speed of things we have built and sent outward. The answer to that question is where the size of the Oort Cloud stops being abstract and starts being something else entirely. Voyager 1 was launched on September 5th, 1977. It carries a golden record, a disk containing sounds and images from Earth, intended as a message from our species to whatever might one day find it drifting in interstellar space. It passed Jupiter in 1979 and Saturn in 1980, using the gravity of both planets to accelerate outward, and then continued away from the solar system on a trajectory carrying it above the ecliptic plane. Today, Voyager 1 sits at roughly 165 astronomical units from the Sun. It is the most distant human-made object ever built. Nothing launched by any space agency anywhere has ever traveled further. It has been traveling for nearly 50 years. It has not yet reached the Oort Cloud. At its current speed of about 38,000 miles per hour, roughly 17 kilometers per second, Voyager 1 will reach the estimated inner edge of the Oort Cloud in approximately 300 years. Sometime around the year 2325, if its trajectory holds. By then, its nuclear power source will have been dead for nearly 3 centuries. Its instruments will have gone silent sometime in the 2030s. No signal will be going back to Earth. Voyager 1 will cross into the Oort Cloud, blind and silent, and no one will know the moment it happens, and nothing on board will record anything about the region it enters. It will then take approximately 30,000 years to exit the outer edge. 30,000 years. 30,000 years ago, humans were painting animals on the walls of caves in southern Europe. Agriculture did not exist. Writing did not exist. Cities did not exist. Every civilization that has ever risen and fallen on this planet, every empire and language and religion and war and invention in all of recorded human history, fits inside a span of time shorter than it would take Voyager 1 to cross the Oort Cloud at its current speed. The situation does not improve with faster spacecraft. New Horizons, the mission that flew past Pluto in 2015, travels at roughly 36,000 miles per hour. At that speed, reaching the inner edge of the Oort Cloud takes approximately 37,000 years. The Parker Solar Probe, which achieves the highest instantaneous speeds of any spacecraft by swinging extremely close to the Sun using Venus gravity assists, reaches speeds of around 430,000 miles per hour at its closest approach. Even at that speed, which no spacecraft has ever sustained over a long journey, reaching the inner Oort Cloud would take roughly 1,500 years. The outer edge would be about 75,000 years away. At the speed of light itself, 671 million miles per hour, the hard physical limit on how fast anything in the universe can travel, the inner edge of the Oort Cloud is still 10 to 28 days away. The outer edge is a year and a half. Light, moving at the fastest speed the laws of physics permit, needs a year and a half to cross what belongs to our own Sun. No propulsion technology currently developed or seriously proposed. Not ion drives, not solar sails, not any of the nuclear propulsion concepts on the drawing board, brings the Oort Cloud within a single human lifetime. A mission launched today would arrive at the inner edge sometime in the 24th century. Crewed by no one, with instruments long since failed, incapable of returning a signal across the distance it had crossed. It is not a destination. It is not a place that exists in any future that can be meaningfully planned toward with the tools currently available to our species. The Oort Cloud is the edge of what belongs to us, and at the same time, the edge of what we can reach. Everything learned about it has been learned from here, from the inner solar system, from the comets it occasionally sends inward like messages written in ice that take thousands of years to arrive. We have never visited. We can't visit within any time frame that connects to anything a living person will experience. The cloud surrounds us completely, in every direction, at distances that defeat every machine we have ever built. And the only window into it is the occasional frozen object that falls our way from that enormous dark, briefly visible, briefly close enough to study, briefly answering questions about where it came from, before it continues on its way, either back outward into the cold or away from the solar system forever. You are listening to these words inside a solar system that is larger than the word solar system was ever designed to contain. Every map you have ever seen, every textbook diagram, every animated model showing the planets in orbit, every illustration with Neptune sitting at the far edge before the black, was showing you the center of something. Not the whole thing, just the warm, lit, inhabited center. The real solar system extends from here to nearly halfway to the nearest star. It surrounds us completely. It is a sphere, and most of it is a place where the sun is not a warm presence, but a distant point of light, barely distinguishable from other stars, exerting just enough gravitational pull to keep a piece of ice in a 4-million-year orbit while providing it no warmth at all. The Oort Cloud does not break human imagination the way a black hole does, through violence or physical impossibility. It breaks it more quietly. It breaks it by belonging to the same star that warms this planet, the same gravity that holds the moon in place, the same sun that every species on Earth has ever lived under, and being so much larger than any frame of reference we have used that the frame itself has to be rebuilt from scratch. The astronomical unit, the unit invented specifically to measure the solar system, reaches its own limit trying to describe what the solar system actually contains. The light year, the unit built for interstellar distances, is needed just to describe what one star controls. Picture a single comet, not the idea of one. The object itself, a few kilometers of ancient ice, formed 4.6 billion years ago from the same cloud of material that became this planet, thrown outward by Jupiter's gravity in the first few 100 million years of the solar system's life, settling eventually into an orbit at 50,000 astronomical units that has continued, undisturbed, ever since. It has been orbiting the Sun so slowly and from so far out that in the entire age of the solar system it may have completed only a few dozen full loops. It sits in darkness, at temperatures just above absolute zero, in a part of space where the Sun looks like any other star. Then something shifts. A star passes close enough to alter the orbit by a fraction of a degree, or the galactic tide, over millions of years, gradually tilts the orbital plane until the comet's closest approach dips inside the inner solar system for the first time. The comet begins to fall inward. That fall takes tens of thousands of years. It crosses the outer solar system in silence. It passes through the Kuiper Belt region. It enters the zone of the planets. The sun grows brighter. The ice begins to sublimate. A tail forms behind it, lit from within by dust and gas that has been frozen for longer than Earth has had complex life. And somewhere on a small rocky planet orbiting that sun, someone looks up at the night sky and sees a faint smear of light and thinks it is beautiful, with no way of knowing what it crossed to get here, or how long it traveled, or how old the material burning away in its tail actually is. That comet is one of a trillion. The rest are still out there, in the dark, on their long, slow orbits, in a sphere that surrounds everything we have ever known. The Oort Cloud is not dramatic. It does not announce itself. It simply sits there at the quiet edge of what the sun owns, and it has been there since before the Earth existed, and it will be there long after anything on this planet has the capacity to wonder about it. That is the honest size of where we live,